Hello there, I'm Michael Fudd, just playing fetch with my dog Luna. I hope that after this lesson you'll be able to retrieve the content, you find it fetching, and if you do, you should be golden. Hello there and welcome. Let's get started with some conceptual data modeling. Lots of stuff to cover today. So let's begin with our agenda. What is conceptual data modeling? These are things we're going to be looking at. Understanding the data requirements, formalizing those data requirements using an entity relationship model, and then taking that entity relationship model and drawing a crow's foot entity relationship diagram. And we'll also kind of peek into some advanced concerns that you need to sort of run through in order to verify that your model's correct. And finally, we'll look at a checklist that you can follow to take your data requirements and build a matching ERD from it. So let's start out with a little review, which is what is conceptual data modeling. We looked at conceptual data modeling very early on in the course, and now it's time to go back and sort of revisit that now that we've spent a lot of time in the weeds learning how to build database objects themselves. Let's think about this question. How do I go about designing a good database? Well, basically, you must first understand the problem, then you can define it. So without understanding what the problem is, it's impossible to solve the problem. And you can't define a problem that you're going to solve unless you understand it. So it's imperative in the analysis phase, in the modeling phase, that you spend time not only understanding the problem, but formalizing how you define that problem. So conceptual data modeling is the process of collecting, then documenting the data requirements of a problem to gain a well-defined understanding of that problem. The goals are to understand the problem and then define that problem formally. There should be no consideration at all for how the solution will be implemented. That is, we don't consider technology, we don't consider what DBMS we're going to use, we don't even consider the implementation model we're going to use, whether it's relational or document or key value or graph. That does not come into play when you're conceptual modeling. The only thing you want to do is gain a firm understanding of the problem and a formal definition of the requirements of the problem. So you may recall this diagram from earlier on in the course in which we looked at the 5 different representations of any database depending on the level of abstraction. So way down here at the bottom, we have the physical data model, that is how that database is actually stored with technology. And we've been living the last few weeks in the internal and somewhat external data models where we have a representation of our database in tables and with foreign keys and stuff like that, because we are implementing it using the technology in the DBMS of a relational model. So at the beginning, we'll get to logical model next week, but at the beginning we have the conceptual model. And the conceptual model is an abstract representation of the data requirements with no implementation of the database itself. And there is no implementation of any given model selected. And I mentioned this before, it's worth mentioning again within context of this slide. You also may recall the database development lifecycle, this is a framework by which we will build a database. We start with planning, which is understanding the problem in scope and boundaries, and then identifying what we're going to do as part of building that database. Then in analysis, we define the problem and capture the data requirements. And the outcome from analysis is the conceptual data model. And this is sort of what we're talking about this week. And then from analysis, you go into design, and then from design to implementation, and then from implementation, you go into maintenance. So you've heard me say this again and again and again. Requirement, 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 requirement. So what exactly is a requirement? A requirement is simply a statement which identifies the needs of a system or an application. Your requirement for a car might be that it seats 4 people. So that immediately rules out cars that only seat 2 people. Your requirement for a car might be that it has all-wheel drive or 4-wheel drive because you live in an area of the world where it snows a lot and you need better traction. So those are examples of real-world requirements that we might need when shopping for a car. When you're building an application or building a system, application, sort of same thing, we have 2 kinds of requirements that we're thinking about. One type of requirement are the functional requirements, and these are the features that will be implemented in the thing that we're building. So if we go back to car, a functional requirement is all-wheel drive. Okay, or maybe another functional requirement might be it seats 4. A non-functional requirement is not a feature, but they're guidelines, behaviors, and expectations. And a non-functional requirement might be that you're going to commute to and from work with this car. Okay, you can commute to and from work with a bicycle, with a car, with a 2-seater, with a 4-seater, with an all-wheel drive, with a front-wheel drive. It doesn't matter. So in that regard, it is a requirement, but it's not a feature of the individual artifact that we're trying to build. Okay? So functional requirements, non-functional requirements. Furthermore, conceptual modeling deals with a very specific type of functional requirement called a data requirement. And a data requirement fundamentally says, what are we storing? Okay, what do we need to store? So let's look at some examples to better sort of help you understand, what's a functional requirement, what's a non-functional requirement, what's a data requirement. So non-functional requirements, let's start over here. Remember, non-functional requirements are not programmable software features, but instead they are metrics and guidelines and expectations. They're generic to any system. So, for example, customers should be able to access the system 24 hours a day, 7 days a week. That could go for any system that gets built. Okay, that's no specific feature. The system should be able to scale to support 10,000 concurrent users. Again, whether I'm doing it by paper or whether I'm doing it electronically, it doesn't matter. It's just a characteristic that I want of the system. It has nothing to do with the individual features per se. So these last ones in italic represent the same sort of idea represented as a non-functional requirement, a functional requirement, and a data requirement. So you might have an application and you require that the images in the application are stored in Amazon's EC2. This should probably be S3, not EC2. EC2 is not the correct technology to use here, but it doesn't really matter. You're going to store the images in the Amazon cloud. Okay, now let's look at some functional requirements. Remember, the functional requirements are the programmable software features of the application. These can be either bought or built, created by programmers or hired out contract programmers, or you could just buy a product that does this. But these represent the individual features of the application that you need. So customers should be able to search the catalog by product name. That is definitely a feature. Okay, you can have an application that doesn't allow you to search. Vendors should be able to build landing pages for each of their products. So if you're a vendor, you can log in and then say, all right, here's this product, soda can, and I am going to build a landing page that talks all about that soda can. Then there's another product I sell is this hand sanitizer. I am going to build another landing page for that hand sanitizer. Those are features of the application. Those are things that people are actually going to do in the application. See how that's different from the system should scale to support 10,000 concurrent users, which is really just a performance metric. Okay, these are things that actually someone has to program into the application. So while the images might be stored in Amazon, vendors can upload their images of their products. That's a feature, right? I want my vendors to be able to log in and upload a photo of this soda can or upload a photo of this hand sanitizer, right? A non-functional requirement is where those photos get stored on Amazon, okay, or somewhere else, right? They said stored on Amazon. So that's a requirement that they have but it's definitely not a particular of the application that gets built. The end user, another way to look at this, the vendor that is taking pictures isn't going to know they're on Amazon and isn't going to care. That's why it's not a feature. Okay, let's dive down into the data requirements. So a data requirement, again, is a specific type of functional requirement that addresses what will be stored. How the data gets stored is not a data requirement. It's actually a form of non-functional requirement. Like, for example, images are how are the images stored? On Amazon. Okay, it's not a data requirement. It's a non-functional requirement. So let's look at it. It's what is being stored. A product should contain name, price, and vendor information. So that panders to what a product is and what makes up a product. Vendors can create one or more landing pages, but a landing page is created by just one vendor. This is a business rule that specifies if you're a vendor, I can create a landing page for this and a landing page for this if I want, right? But if I make a landing page for this, that belongs to me, the vendor, right? So that's a business rule that's established through a data requirement. Okay, that explains what the system should do, not how it should do it. Here's another data requirement. A product can have several images associated with it. So I can take an image of this like over here, or an image like this, or an image like this. I could take lots of different images of the same product, okay, on that one landing page. So if we look at the italicized ones at the end, right, this is a data requirement. It specifically says a product can have many images. This is a functional requirement because it says a vendor can upload several images. And then this is a non-functional requirement saying that those images are stored in Amazon. So that's the difference between a non-functional, functional data requirement. All right, next, it's time to talk how we gather data requirements. So there's three facets to requirements gathering. One is identifying key stakeholders. The other is identifying the dependent systems. And the third is using the information from the key stakeholders and the information about those dependent systems to identify scope and boundaries. And scope and boundaries is really important because this is going to sort of give you an idea just how large of a project it is. You can certainly rein in the size of a project by narrowing the scope of the project that you're trying to, of the system that you're trying to build. So let's talk key stakeholders. A key stakeholder is any person with an interest in the outcome of the system. So they are going to use the system, or they are going to benefit from that system. So end users and their managers are always key stakeholders because these are people directly involved with the system. Why are the managers part of the key stakeholder conversation? Because there is a chance that through the development of the system, people's job roles and responsibilities will change. What they do day in and day out may now all of a sudden be different, and that's why you need to get management involved. So it's important to make sure that you keep that dialogue going between not only users, but their managers and potential ways that work may change. Obviously involved in this as well are the development team, because these are the people that are going to design the application, maybe build the application, or supervise contractors who will build the application. And then most importantly, there are those who will maintain and support the system. So these are your IT people, your help desk people, your database administrators, your systems administrators. These are the people that are going to be responsible for making sure that the system stays up and running once it gets built. You definitely need to have a conversation with these folks and make sure they're involved directly in the process. As a matter of fact, there's a whole discipline called DevOps, and DevOps really is about making sure that the development team and the operations team, that is those that will maintain and support it, have a vested interest in making sure that the application succeeds. Too often, these two groups work independently of each other and develop factions and have the it's not my kind of problem. It's not, that problem is not mine. You got to blame the development team for that. Or that problem isn't mine. That's a problem with the way that the systems administrator is running the system. So rather than deflecting blame, the idea is that both teams take a very vested interest in making a system work. And that's basically what DevOps is about. Then finally, the last one to consider are external entities. These are external facing organizations and users. These could be suppliers and vendors and partners and cloud companies and things like that. There could be a lot of external agents that have a say in what happens with the system and how it ends up getting developed. So let's talk about dependent systems. When you're looking at dependent systems, you need to think about the inflows. That is, what other systems provide data to the system that you're developing. And then you need to think of outflows. That is, what other systems are the consumers of the information that will come out of the system I'm developing. Most of the systems that you are developing, they already exist in one way, shape, or form. You're just either improving them or enhancing them or taking something that was done manually and now systematizing it. And in either of those cases, there's always going to be data inflows and outflows, whether they are manual data inflows or not. Where inflows and outflows are important is if it's a manual data inflow, then you may have an issue if you automate or systematize the product that you're developing. You may have to consider how you can automate some of the inflows. Like maybe you're building some kind of expense reporting system, and currently the expense reports, the inflows are coming in as paper. You may want to think about, as a way to enhance the system, redesigning it so that paper is no longer used. If paper must still be used, then you might have to figure out a way to automate the paper inflow. That is, give users of the system that you're building a means to scan in that paper and digitize it. Okay, just some of the thoughts that I have on dependent systems and inflows and outflows. Also, one of the dependent systems you need to think about are all the underlying infrastructure that supports your system. For instance, your system may use a DBMS. It may run as a web application. It may run on Linux or Windows. It may run on a multitude of systems. It may run on Kubernetes. So knowing that infrastructure, the current infrastructure that's being used, and maybe even the proposed infrastructure, are considerations that you need to take into place, because they may unearth additional non-functional requirements as well as some functional requirements. So once you have an idea of the dependent systems and the key stakeholders, then you can start to think about reining in the size of the system with scope and boundaries. So basically, we're talking about what is outside what will be done. So you have an idea of what you want to do, what is clearly outside of that. Then you have to think about prioritizing all of these requirements that you have. Which ones are critical? Which ones are low importance? Which ones are maybe not relevant? Necessary, like someone thinks they're necessary, but they're really not. And then that way, when you prioritize your requirements, you can then have a hard conversation about how much of an investment you want to make in the system, because ultimately you are constrained by people, money, and time. And you certainly cannot be in the business of building systems out independent of any resource constraints. That is very impractical and not economical at all. So you really need to think through, what are my critical requirements that are necessary to making what I would consider a successful system. I like to joke around and call it the low-hanging fruit, right? The stuff that you can easily do and it will have a great amount of impact. those things might make it into scope. Always consider an iterative process here, right? So you might say these things are part of phase 1, and we'll release phase 1 to users, and then we'll do these things for phase 2, and we'll release those to the users. And that way you can build what's called a minimum viable product, something just done enough so that it can be used. I always joke around, my metaphor is the Death Star. If you watch Star Wars, in the Empire, in Return of the Jedi, the Death Star is not completely built, but it still works. So that's sort of the idea behind minimal viable product, is get something that works, that's not completely baked in, so that you can get people using it, get feedback, and make improvements to it. And so versioning, saying, these particular requirements will go with version 1, these particular requirements will go with version 2, version 3, and then setting up a project plan that accommodates those different versions will go a long way to showing progress and not taking years to do it. There are a variety of requirements gathering techniques that you can use to collect the data requirements, the functional requirements, and the non-functional requirements of the application that you plan to build. You can interview the key stakeholders. You can survey key stakeholders, but that seems to be impersonal. A better way to go about that is to not survey the key stakeholders, but those external entities. Like, if you're building a new Twitter, you might want to survey your customers, because you can't go about interviewing every single customer in Twitter, right? So if you're building some kind of invoicing application, you might want to survey your customers, right? You don't want to interview customers. That's probably too time consuming, but you would interview the employees that will use the system. Excuse me. You can also do some data collection, where you might look at invoices and other artifacts from the current system to get a better idea of what kind of data needs there are. You can do observation. Observation is where you passively watch people use and interact with the system. This can be done in a variety of ways. You can literally stand over someone's shoulder and watch what they're doing. It's kind of creepy, but it's one form of observation. It was the old school form of observation. You can also put a camera and bring people into a room that's filmed and just sort of watch their use of the system, or use screen recording software to observe how they use a current system. One thing that I always like to do when gathering requirements is actually use the system. Sort of go through the current system myself, try it out, see what happens, and make notes about what I think is happening underneath the hood. It's a really great way to black box explore a system that you don't have access to but need to somehow improve or develop. And when I say you don't have access to it, I mean you don't have access to the code, so you don't know how the behaviors are. You only have access to the results of the code. One of my favorite requirements gathering techniques was the job shadow. You walk a mile in the key stakeholders' shoes. You learn what it is they do and how they do it. And one of the reasons why I really like job shadowing as a requirements gathering techniques is you also see ways that you can use business process improvement to not only build a system to help people do their jobs better, but also in general how to change maybe interactions and workflows within your organization so that just things work better. For instance, you may have in your job shadow encountered that there's an extra 2 or 3 steps with a process that can be eliminated as the process gets simplified. It involves no technology. It just involves maybe changing around how things are done. You also might notice as people use forms or applications that there's always parts that they don't bother to fill out. So through that job shadowing, you might save a lot of time and resources by not having those things on future forms. Another very interesting approach to requirements gathering is joint application design. And basically what you're doing is you're having a few meetings where all the key stakeholders get together, you all get in a room, and you work through some of these things such as observations and data collection together. This gives the users involved in the system a sense of belonging to the new system that's being developed. It doesn't feel like someone's moving their cheese out from under them, so to speak. It feels like they are part of the process. The disadvantage of joint application design is it's really expensive to put everybody in a room. You're taking people away from their daily activities and jobs. It can be time consuming. It can be unnatural at times because people, you don't get to see how people actually do their jobs. You're seeing how they do their jobs when they're performing in front of an IT team and a development team. So in that regard, it can be a little unnatural, and it takes a certain type of climate to get joint application design work. Your organization has to have the right kind of mindset to make this work. If it does, it's a very powerful way to gather requirements and get people who are going to end up using the system really on board with it, to show them that you're actually making improvements and not disrupting their work lives. So one thing I cannot overemphasize is the importance of understanding the problem domain. You can't solve a problem you don't understand. Plain and simple. So if you're trying to build a better accounting system, you need to understand accounting. Okay, if you're building an invoicing system, you need to understand invoicing. Sometimes this is pretty easy. So it's, you build one invoicing system, you built them all. It's really just a matter of understanding the nuances of the organization you're working with and how they prefer to do their inflow, their process flows and things like that, and what data is inflowing and what information is outflowing. Where it becomes a challenge is when you're trying to implement something that's way outside your problem domain. For example, you might be trying to implement an inventory management system for a group of physics professors, and they have lots of weird type of products that you don't understand what they are, like these lenses and things like that, and you don't know how they go together. I can't even speak well to it because I don't even know what it is. And so that ends up being a problem unless you truly understand their terminology and how to go about solving the problem from their perspective and how they're going to use these things. It ends up being a very difficult uphill climb for you, and also it sort of takes a hit to your credibility, right? So this is where it's important, as I'm reminded of when I was trying to build Salesforce automation software for a company I worked for. I didn't understand a lot of the sales terminology. I didn't understand what our salespeople were selling. And that was a big problem with credibility. So I did some job shadowing. I was a salesman for a week. And I went around with different salesmen, and I saw how they did things. And I saw their challenges. And I saw that certain things and certain types of technologies weren't going to work because of how they did their jobs. And that's something that you can't really underestimate as you go about building a system. You don't want to spend a lot of time and energy taking a requirement and just blindly implementing that requirement if the end users don't have buy-in to that. If you're going to say, well, I'm going to give everybody the ability to be able to print out quotations from their cars. Well, does everybody want to carry a mobile printer around with them? Is that necessary? Wouldn't it be better maybe to just have a way to email the quotations to the customers, and then they can say, well, I just sent you one, check your phone, you have my quote. And that way you don't have to print it out and hand it. But again, it depends on the culture. It depends on the key stakeholders, and those are usually the direct key stakeholders. It also depends on your budget, depends on your time, depends on a lot of things, but most importantly, you have to understand the problem. You have to understand the problem you're trying to implement. All right, let's talk a little bit about taking those data requirements, and building an entity relationship model from the data requirements. Basically, there's 3 steps. You identify the entities, you identify the attributes that belong with each entity, and then you identify the relationships among the entities. Now, I want to emphasize, again, we're not modeling the real world. So when you have a customer entity, you're not just going to put in anything you think goes in the customer entity. What you put in the customer entity as attributes should be found in your data requirements. As you build what you think is a customer entity and you have attributes in there, you should always use that as a communications tool back to your key stakeholders to ensure that the attributes that you're collecting are what they need. Do not collect more than what people need, because for every attribute you have, someone has to enter it. It has to come from somewhere, and you don't want to be in the business of having extra. Also, same thing with relationships. You're not modeling the real world, you're modeling the business needs of the application that you're creating. So, just because, a user drives a car doesn't mean that that's part of the process that you're trying to solve. Again, when I was building Salesforce automation software, our salespeople were given a car lease that they can have so they can drive around, and they had mileage reimbursement and things like that. But that was out of scope of what we were trying to accomplish. And while I certainly can see that one salesman has a car assigned to them, and then every week they submit a mileage and reimbursement report, and those are data requirements, that stuff wasn't part of the problem I was trying to solve. And so that's really important, and something that cannot be overstressed here is keep it within the scope, keep it within the boundaries of the problem you're trying to solve. Do that, ER modeling becomes very simple. So, step one, identify the entities. Entities are the things we need to store. These should always be data as objects, meaning they should be these composite type attributes, right? So we remember there's data, there's a data that's atomic, and then there's the data as object, right? And we're talking about multiple atomic elements that build up one piece of data. That's what an entity is. So examples of entities are people, places, things, and events. Entities are individual things, not collections of things. So an entity would be, a book, or an invoice, or this can of soda. An entity set is a collection of entities. So if I'm looking at a shelf and there's lots of different cans of soda on the shelf, that's an entity set. Any one of those cans I pick off the shelf, that ends up being an entity. Likewise, behind me here, you see there's a bunch of books, right? One of those books is an entity. All the books on the shelf is an entity set. So entity, one thing. Entity set, collection of real things. If you think about it in terms of implementation, if you end up implementing this as a database table at some point, the entity is a row in that table, and the entity set is the table itself and all the rows in the table. Okay. So fundamentally, that's where you need to be thinking when you're thinking of an ER model, is you're referring to an entity, but you're saying any one generic one of these things from the entity set, what are its characteristics? But you have to think singular, right? Don't think in terms of the thing, right? Think in terms of any one of those things that I pluck from the set. What are the characteristics that it has? You do that, you're going to be successful. How about some examples? So people entities, you could have a customer, employee, or a student. Right? These are all examples of entities as data as object, because a customer has a lot of different things about a customer: name, email, phone number. Student might have GPA, major. Then you have entities like places, like department, airport. Airport might have latitude, longitude, street address. Business might have street address, name of business, domain of business. Like, are they in the business of shipment or redistribution or manufacturing? What kind of business is it? Entities as things like computers, right? How much RAM does it have? What's the CPU? Vehicles, make, model, number of passengers. Generic equipment, like you might have a hammer, wrench, things like that. And then entities as events, like making a payment, booking an appointment, when a car gets in an accident, right? All of these are examples of entities, and they're all examples of data as an object, right? Because each of these things has some kind of attributes. If your thing that you're considering to be an entity does not have any attributes, then it's not an entity. It needs to have attributes. So let's identify the attributes of each entity next. So entities are composite objects, therefore they should have attributes. And the possible attribute properties that we assign to each attribute are these. So one of your attributes that might not have any of these properties. But for every attribute, you need to ask yourself, is it a natural key or a business key? If so, it gets the unique attribute. Is it required? For example, this soda can, right, has a number of calories on it somewhere, right? And it also has a UPC code. Those are required. Every can has that. Composite would be, for example, you have an address or a name, something that you want to represent as one attribute, but really it should be broken down further. It maybe isn't its own entity per se, but it just, you want to represent it as one attribute just to sort of simplify things. You don't want your conceptual model to be too down in the weeds. It makes it very hard to digest when your conceptual model is extremely detailed. So it makes sense to use composite attributes. A derived attribute is an attribute that's calculated from another attribute. Whether or not it's stored is irrelevant. Okay, what derived means is that the value can be calculated from these other attributes. So if you have an invoice, the total amount on the invoice is obviously calculated from things like the tax, the shipping, the subtotal of all the products purchased, right? That would be an example of a derived attribute. Would you store that value in a table someday? I don't know. I don't care. That's not the point of a derived attribute. Derived attribute is really just to indicate that the inflow, it doesn't come from someone typing it in. It gets calculated. A multi-valued attribute is another form of convenience attribute similar to composite, but what it does is it says this attribute could have more than one value. So an example of that might be the number of colors on a can. Like this can here, it just has orange and yellow on it. So those are the two colors on this can. It doesn't make sense to make its own entity for just the colors, things like that. It's kind of overkill. So you just want to put multi-valued in there. This sort of happens with things like, like I said, with colors. It could also happen with more sophisticated things like emails or phone numbers, stuff like that. Let's do some examples of attributes. Your customer attribute might have, or your customer entity might have these attributes. It might have an email, which is a natural key, unique, and it's required. Your name might be composite and required, which means it would be first name, last name. Address might be composite. Phone number might be multi-value. You might have a home phone, cell phone. You might have a payment entity that has a date of payment, which is required, an amount which is required, and then a payment method such as credit card, check, or cash, which is required. Generally, when you're building data requirements, you would describe each of these attributes in detail, as you'll see further along when I do another example. Next, you should identify the relationships among the entities. And so we got to get some terminology out of the way. Entities which take part in a relationship are known as the participants. The relationships are expressed in two directions, from one participant to another, and then from that other participant back to the original one, forward and backwards. We have to do this because cardinality represents the minimum and maximum number of participants, and we must check the cardinality on each side. And the maximum cardinality on each side identifies the relationship classification. And there are three basic classifications: one-to-one, one-to-many, and many-to-many. Sometimes represented as MM, other times as MN, but it still means many-to-many. So here's some examples of relationships. Here's a one-to-one classification. So again, you read it forward, you read it in reverse. That represents the entire relationship. So a resident of a state is issued 0 or 1 driver's license. 0 or 1 is the cardinality. 0 is the minimum cardinality. 1 is the maximum cardinality. Driver's license is the other entity. So how does this work? Imagine an entity set of everybody that lives in the state. One of those residents might not have a driver's license, 0 driver's license. Another resident might have 1 driver's license. There is no resident that has 3 driver's licenses, so it's not many. Now you have to consider the reverse to finish the classification. So this side of the classification is 1. A driver's license is issued to one and only one resident. This makes sense because if you look at a driver's license, there's only one person on that driver's license. It doesn't go to 3 people. But there's never a driver's license that doesn't have a resident on it. Therefore, driver's license issued to one and only one resident. And then this side of the cardinality is 1. So the upper bound of each tells you the cardinality, 1. Or the upper bound of each tells you the classification, 1, 1. Here's a one-to-many classification. A customer submits 0 or more payments. So you sign up, you're a customer, you haven't submitted any payments yet. Somebody else might be a customer for years and they submitted like 20 payments. Okay? So the cardinality is 0 or more, and the classification on this side is many. Now this one says a payment. So if you're a particular payment, that payment was submitted by one and only one customer. It's not like 3 customers could submit the same payment. That wouldn't make any sense. Therefore, the cardinality on this side is 1 and only 1, and that makes this relationship classification 1 to many, or many to 1, same thing. 1 to many to 1, same thing. Let's look at a many-to-many classification. So a student is a member of 0 or more clubs. So Andrea is a member of 4 different clubs. Tommy is a member of no clubs. Now, if you're a club, that club enrolls 0, it's a brand new club, there's nobody in it, or more students. So one club might have 200 students in it. So this is considered, because it's many at the top end of the cardinality, this classification is many to many. So again, remember, relationships, read them in both directions. Pretend like you're any one of the entities out of an entity set, then ask yourself the question. Then pick another entity out of the entity set and ask yourself the same question, just to see if you've got the cardinality right. So, when capturing your ER data requirements, include contextual descriptions of the entities. That is, explain what a product means. Product is an item for sale in our catalog, right? This should be, if you don't know, ask. So during the interview process with key stakeholders, I might hear the word payment. And I'll say, can you define what payment means to you? And then I might talk to another key stakeholder, and they don't even mention payment. They mention invoice. And then I say, can you explain what invoice means? And they give the same definition as payment. So one person calls it an invoice, one person calls it a payment. What is it? That's why, as an analyst, you, 1, interview several people, and 2, need to really get a definition of these entities so that you can figure out if you're talking about the same thing. You should also include data definitions for the attributes. So you might say a product UPC. So there's a UPC code on every product. That is the product universal product code, and it's globally unique. So this is a description of the attribute in an entity, and these are the properties of that attribute. And then this is just some plain old text that explains what it is. Okay, that's important, especially when you're dealing with composite attributes. You can say this is a composite attribute, and it consists of everything you need for someone's full name. So last, middle, first. When you specify data relationships for both participants, use a verb which describes the business rule. Do not make up your verbs. Don't say, hey, a vendor has a bunch of products. That's not the business relationship. The vendor supplies the products, right? So the vendor does something with the products. They mail them. They mail them to your company, and then your company puts them in the warehouse, right? If you don't know what the verb is, ask someone. Say, what does the vendor do with these products? And then let people tell you. Well, they supply them, idiot. And you say, oh, okay, I got it. Don't be afraid to do that, because you're learning their domain knowledge and then representing their domain knowledge as a data model. And it just takes time and practice to get the terminology down, especially when you're learning about their system and how it works. So the other thing you want to make sure you do is also do it in both directions. This is not done in both directions. Should be done. Vendor supplies 0 or more products. Product is supplied by one and only one vendor. Make sure you do the cardinality in both directions to complete the business rule. So let's do some sample data requirements for like Netflix. Let's just pretend that we're dealing with Netflix and their payment system. So we have entities like customer, external facing user of the service, payment, monies owed for using the service. We have attributes. Example for customer, we might have email, right? You sign up with an email. You would have a billing address, right? This is the typical international mailing address format used for billing a customer. Then you might have relationships like, a customer submits 0 or more payments. A payment is submitted by one and only one customer. So this is an example of building data requirements. First, you build the data requirements. Then, after you build the data requirements, you build the diagram. The diagram is a subset of the data requirements, and it doesn't address all of the data requirements. It only visualizes them so that they're easy to explain. Mostly what you're looking for out of the diagram is a capture of the entity attributes and relationships, but all these nuanced definitions will only be found in the requirements themselves. So here's an example of the same thing, but implemented by listing the requirements in a spreadsheet. This is one of my favorite ways to make data requirements is I have a spreadsheet and then I just kind of fill it out like this. So I have a customer and then here's all my attributes and then here's the properties of the attributes and then here's the description. And I find that while I'm working and interviewing people and job shadowing, I'll just write notes and then I'll go back and I'll start to fill in that spreadsheet later from my notes. And I'll just, sometimes I'll doodle in my notes. Sometimes I'll just draw. Sometimes I'll record the session and listen to it later. But the point is to try to leave no stone unturned and capture as much as you can. And in the process, not forget anything, because that would be bad. And then as you build out the requirements, you might then prioritize them. But you always want to make sure that you get everything and don't leave anything out. So I would do this for entities, and then I would also do one for relationships where I have the overall relationship and then the entities involved, and again, both directions for that relationship. So in essence, this is the same as this. It's just another way to represent the same thing. All right, let's practice drawing crow's foot ER diagrams from our data requirements. So let's talk a little bit about ER diagrams first. ER diagrams are taking your data requirements and then drawing a picture with them, right? It's a documentation and communications tool because, again, a picture is worth 1,000 words. It's so much easier to explain and describe a visualization than it is to just look over a spreadsheet of requirements, right? There are a few different notations you can use when drawing ER diagrams, such as the Chen notation, the Bachman notation, unified modeling language class diagrams, and crow's foot notation. We're going to use crow's foot notation because it's popular. A lot of the DBMS tools use it. It's easy to learn. It's very intuitive for others to read and understand. It's a really good model, a notation to use for ER modeling. So let's take a look at basically what a crow's foot looks like. So at the base level, you have a box. That box represents your entity. At the top of the box is the name of the entity. It should always be singular. Shouldn't say salespeople, or it shouldn't say customers, because customers would be an entity set. It should be a thing, customer. And then you list underneath it the attributes and then describe the properties. You don't have to describe the properties. I like to do that so that when I'm talking to the customers, I can make sure that I'm doing it right. For example, I may talk to somebody who's involved as a key stakeholder with this particular process, and I would say, is your username unique? Like, do you and somebody else have the same username? And they'll be like, no, Mike, no, we don't have the same username. And they're like, aha, I know, I got that requirement properly. And I might say, all right, well, your name, right? How would you like to store your name? Probably like first name, last name, or do you need a middle initial or what, right? And so that's composite, and then I would break down in the data requirements, not necessarily in the diagram, but in the data requirements, how that name is broken down specifically. We have other attribute descriptors like required, right? Derived, as we talked about before, and multi-valued. So in this case, where it says certifications, you might have like 4 or 5 different technical certifications that like are part of you being a salesperson. Like you're certified to sell this equipment or that equipment or that equipment. You've been trained to drive this or operate that. And those certifications are useful when you're trying to match a salesperson to a lead, right? Someone who wants to buy a particular type of equipment. You want to hook them up with an expert. So that's why you might want to have certifications. It doesn't need its own entity per se, because it's just got certifications. There's nothing else with the certification. There's just that. So relationships. Relationships, a line connects the participating entity of a relationship. So customer and quotation, they're related through a business rule. The business rule is right in the middle. Receives. Okay, so a customer receives a quotation from a salesperson. If I have that quotation might be received by that customer. And then the cardinality is displayed on each end of the line. So it's read as follows. You'd say customer receives 0 or more quotations. And then you'd say quotation received by one and only one customer, right? The cardinality is always next to the second entity. Okay, so you do not read it, customer, one and only one, receives 0 or more quotations. That's not how you read it. Because remember, entities are singular. You're saying if I pick a quotation out of a hat, here's all my quotations. I picked this one. Oh, it's been assigned to one and only one customer. But a customer could have 2 quotations. And thus, it's many. Again, when you're dealing with relationships, you must pretend to draw from any particular entity from that entity set. Usually, I have to do this a couple times in my head to get the cardinality. I'm like, well, there could be a case where one entity from the entity set has no quotations. And then it could be another case where one entity from the entity set of customer has 1 quotation. And then there could be another case with a customer entity from the entity set where they have 10 quotations. Therefore, it's 0 to many. The minimum cardinality is 0. The maximum is many. You're only really concerned with 0, 1, or many. And at the minimum, it's only going to be 0 or 1. And at the maximum, it's going to be 1 or many. So again, here are your valid cardinalities. 0 or 1, 1 and only 1, 0 or more, 1 or more. And you could say 0 or many, 1 or many. I like to say 0 or more. It's just how I do it. So, drawing relationships from requirements. I've already said this about 4 or 5 times, and that's because it's tricky. And this is the thing that trips a lot of new data modelers up. So, it's deserving of our time. Let's suppose a foo snarks at 1 or more bar. You would initially represent this as from left to right. Foo snarks at 1 or more bar. Now you have to write the relationship in the other direction. Bar snarked at by 0 or 1 foo. Bar snarked at by 0 or 1 foo. Together, this is what the relationship looks like. Foo snarks at 1 or more bar. Bar snarked at by 0 or 1 foo. Okay? So you don't ever want to draw them like this and that. You want to draw them like this, right? This way, when you read to the right, it's the top business rule. When you read to the left, it's the bottom business rule. Basically, that's it. All right, let's draw a crow's foot ERD using these requirements. Let's go into diagrams.net and draw that. So here I am in diagrams.net, and I'm just going to create a new diagram and just blank diagram. This is always the way I start it, blank diagram. You'll see over here on the left, there's all these different widgets that you can pick from. What we want is entity relation, and you could probably use this box here, but the better thing to do is to use this guy here that says entity. Reason this is great is because it already has the top for you where you can put the name of the entity, and there's a place underneath to add the attributes. So I'm going to add my two entities. I need a customer entity, and I'm going to zoom this in. And then I'm going to add in my payment entity. And then I'm going to fill in my attributes here. You can see this is not a hard process at all. Email, and it's required and unique. I'm just reading off the slide from the PowerPoint. And then billing address. And that is required in composite. If you want, you could do it like this. Name, required, composite. You can do it that way too. I just like to keep it short and sweet. And then phone. You might think, are these going to be like fields in a table? At some point, they are going to be columns in a table. Right now, they're not, because that takes into account an implementation, and we ain't worried about an implementation right now. We're just worried about capturing the requirements, the data requirements, and documenting them. I can implement this same customer in MongoDB, which doesn't have tables. I can also implement it in Cassandra, which only has one large table. I could try to do it in Redis. That would be very hard. I could definitely do it in Neo4j, a graph database. So there's lots of different ways you can implement it, but let's not think about implementation right now. Let's just capture the data requirements. So customer, payment, and then over here the payment attributes were date of payment, and that was required. And then there was an amount, and that's required. And then there was a payment method, and that was required. Now, a couple things. If you fill these out and there's not enough room like that, just resize it, right? Just take this guy and resize it so that it fits. Likewise, if you have too much room, you can always make it smaller, right? Now, to make the relationship, you see when you hover over the guys, you get this little arrow here. See that? When you drag, it makes an arrow. See, and it's attached here, and I can attach it to itself if I want. Or I can come over to this guy and attach it. And then once it's attached, see the line follows. Now let's change this line to be the way we want. Now this lets us control like what the line looks like. See, it's using hard angles, but I can also make it use curves, or I can make it use like a freehand, angular, or a straight line, right? And this will, see, it's just using a straight line now. And then let's change the line ends. So I'm going to jack these line ends up. I usually go to 12 point. And then I will take one end. It says customer submits 0 or more payments. Customer submits 0 or more payments. So this end should be 0 or more. And the other end is payment submitted by one and only one customer. That end. So that I add submits, submitted by. I might want to make that bigger. There. And there you have it. I just drew a real quick ERD. Now, one thing to note is when you add the next entity, and let's suppose you want to draw a relationship between these, it will automatically use the last style of line that you chose, which is actually nice. Right? So, I don't have to change much about this line. It's the preference, the way I want the line. It's the same size. It's the same. It's a straight line like I wanted, and it uses the cardinality I wanted. I can change the cardinality, but it uses what I asked for originally. Right? And I can change that to one of these guys, and then the next one I add will be one of those. See? Okay. So that's basically it. That's drawing ERD diagrams with diagrams.net, which is a really cool application. It runs in the browser. It's open source, but you can also download a version, and the version you download will run on your desktop. So it's kind of neat. And then you can just save it, file save, and give it a name. Sample diagram. Cool. All right, let's talk about some special cases. There's really just 3 of them. One of them is called a weak entity. So anytime you have a one-to-many classification, you may have a weak entity, and you should always check every one-to-many to see if the entity is weak. And generally, this can be done by just asking the business user or whoever the key stakeholder is some questions about that many side of the relationship that you've identified. So a weak entity basically means the entity on the many side cannot exist without a participating entity on the one side. In this case, the relationship is said to be existence dependent. One entity cannot exist without the other. So here's an example of 2 relationships. The first relationship at the top between entities A and B is an example of a weak entity and an existence dependence relationship. And here's how you know that. This one and only one on the other side of entity A says that entity B is weak. Think about it. If you exist over here as entity B, then you will have a one and only one corresponding entity A. Therefore, it doesn't make sense. You cannot have something over here that isn't also over there. This is more than likely the case that you will see. Most entities out there are weak. You will find very few entities that are not weak. And a not weak entity has a 0 or 1 on the one side of the one-to-many. And what that means, in essence, is that this entity Z can exist without a corresponding entity Y. So let's do a real-world example and discuss why this is something that you need to consider. In this example, I have the same relationship. Team, player. Team rosters 0 or more players. Player assigned to one and only one team. This one says team rosters 0 or more players. Player assigned to 0 or 1 team. In essence, they're the same business rule, but there's a subtle difference, and it's very important. This one up here says every player must be assigned to a team. If you put a player entity over here, you can be assured that they are on a team because of this one and only one. This one down here says not every player must be assigned to a team. There could be a player over here that isn't on a team. So which one is right? Obviously, this one is a weak entity. This one is not a weak entity. Which one is the correct one? That is going to depend on your data requirements. What are you modeling? Is there a situation where you need to have a player and at some point in time they will not have a team? If that's the case, then you need to model it this way. If you want to have a stronger type of rule that says there is no way I will ever have a player exist that's not on a team, then you want to have this rule up here. So that's what you need to do. That's the question you need to ask. It's just a double check on this side, the one side of the one-to-many, to make sure that it really is this way. Let's talk associative entities. So associative entities, they are a many-to-many classification which contains an attribute. This must be resolved to its own entity, and the name of the new entity is called an associative entity. And the associative entity is always a weak entity. So let me give you an example. I have entity A, entity B, and some relationship X, and there's some attributes you want to put right there. So the fact that A and B are related, there's some data about that I would like to stick right there. Okay, and this will happen to you when you're doing your modeling. So what you need to do in this case is you resolve it to an entity. You put the attributes in the entity, and then this thing down here is now the associative entity. And how do you resolve the many-to-many to what you see here? It's very simple. The cardinality on the associative entity matches that on the original relationship. So if you go this way, the cardinality is one-to-many. That goes over here. See that? If you go this way, it's zero-to-many. That cardinality goes here. And you might say, does that really make sense, Mike? I want you to think about it. So this says entity A, some relationship, one or more B. This says entity A, to be in this relationship, needs one or more. That's true because what's it in a relationship with? Entity B. So that's how you resolve the many-to-many properly to the right one-to-many and include the associative entity. So here's an example of an associative entity and resolution. So you might have product appears on 0 or more invoices, and an invoice lists 1 or more products. And you might notice that in this relationship, you need to include attributes like how many product were on that invoice, a quantity, and was there any discount applied to that product on that invoice. These are attributes that need to appear here. So what I did was I made an entity called invoice product. Now this is a common way to approach the problem is you don't want to call the entity appears, so you call it invoice product, or you could call it product appears on invoice or something like that. It should have usually product and invoice in the names. So contextually, where the associative entity lives. Appears is too general of a business rule to satisfy that. So I have my associative entity. Now it's weak. One-to-many, weak. And then furthermore, this side is 1 or more. So this side is 1 or more. This side is 0 or more. So this side is 0 or more. If you think about this line extending 0 or more, line extending 0 or more, line extending 1 or more, line extending 1 or more. That's how you properly resolve the associative entity. Now, sometimes there are relationships that are reused among several entities, and this can be difficult to notice. For example, a doctor visits a patient, and a patient visits an office, and a doctor visits an office. And, one doctor visits many offices throughout the day or the year or whatever. An office room can be visited by many doctors. A doctor visits many patients. A patient visits many doctors. Okay, so you see what's going on here. This is the same relationship. So this needs to be resolved. You shouldn't leave it like this. If you don't resolve it, watch what happens. If you don't resolve it, we might say, all right, there's an attribute associated with this visit, the date and time of the visit. So in which case you would resolve all of those many-to-manys using the associative entity rule and get this. So doctor, patient, here's the visit between doctor and patient. Patient, office room, here's the visit between patient and office room. Office room, doctor, here's the visit between office room and doctor. But these are the same entity, right? If you think about it, within context of the problem, why is the doctor visiting the patient? They're in some office room. Why is a patient in the office room to visit a doctor? Why is a doctor in the office room to visit a patient? So whenever you see this, you should represent it as follows. You should treat it as a associative entity between all three entities in this case. It could be 4 entities or 5 entities. That's why I say N area. It could be tertiary, quaternary, etc. And basically, you treat visit as the associative entity, and then all these others are one-to-many. And then it might not conceptually sit well with you, but it will implement correctly in a variety of databases. Think about it this way. One doctor, Dr. Fred, makes a visit. He's visiting one patient in one office. But, a patient has many visits, but in that many visits, they might be in different offices and different doctors. Right? So it works. It works. It looks weird, but it works. And that's the proper way to resolve those tertiary, quaternary relationships, is with building an associative entity and then doing your one-to-manys. Okay, a lot to unpack from here. Let's sum up. Data requirements are functional requirements which address how we store the data. No, I'm sorry. They address what we're going to store, not how we're going to store it, right? So data requirements address what data we're going to store. Data requirements can be formalized using entity relationship modeling, and I like to use a spreadsheet to do my entity relationship modeling. ER diagrams could then be drawn from the ER model. One-to-many relationships should be checked for weak entities. Many-to-many relationships should be checked for associative entities. Redundant relationships across multiple entities is an indication of a N-area relationship, which should be represented with an associative entity between all the other entities that are related to it.